So the question here today is, which of these is a systematic name for the compound represented below? Your first step is to identify the longest carbon chain. So we're going to start counting from this point here. So this would be 1, 2, 3, 4, 5. If we start counting from here, it'll be less. It'll be 1, 2, 3, 4. If we go this way, it's 1, 2, 3, 4. So our longest chain is this one right here. That's going to be our main carbon chain, and we know that it's 5, so the name is going to be pentene. We have a little carbon attached right here, and it's 1, so the name for that is methyl. So we know that it's going to be methyl and pentane, but you have to see where it's attached. You always want to have the shortest one, so you want to make sure to count from both sides of the chain. So if you start counting from here, it's 1, 2, 3. It's going to be in the third one. And the same if you count from this side, it's 1, 2, 3. Right here it doesn't make a difference, but just make sure you count from both sides. For this particular problem, they want to know the Lewis dot symbol for S-2 ion or sulfate ion, and they give you these answer choices. Right off the bat, you know that this answer choice is wrong, as well as this one, because these represent bonding. This is not bonding with anything, so you know that you're only going to have electrons flying around your ion. First thing you do is you go to your periodic table and you find your sulfur ion. From there you get that it has 6 valence electrons. But you have your -2 here, which means you're going to add 2 more valence electrons, giving you a total of 8. So you want to start drawing your 8. You know that the rule, the octet rule, is that one layer is 8 electrons, so you know it's going to complete the whole thing. But you want to make sure that people know that this is a special case because you have a... In this problem, they're asking us to write the Lewis structure for H2CO3, which is carbonic acid. First thing you want to do is break them off separately so you can know how many electrons you have in total to work with. So you have your H2, which will be 1 times 2, will give you 2 electrons. Then you have your C. You go into your periodic table, you know that it has 4 valence electrons, plus your O3, which will be 6, because oxygen has 6 valence electrons, times your 3. This gives you a total, 6 times 3, that's 18. So this gives you a total of 24 electrons to work with. So you want to start with your center that connects everything together. It's going to be your carbon, which has 4. Usually you would put 1 on each side, but it will connect because it has a double bond with oxygen. You see right now. You're going to have another oxygen right here. You have 3 oxygens, so you're going to be surrounding your carbon. And last but not least, you're going to have your hydrogen. One here, and 1 here. You know that hydrogen has 1. and all your oxygens have 6. So you're going to have 1 that bonds here, 1 that bonds here, that's 2, 3, 4, 5, 6. Right here, as I said, is going to have a double bond, so it's going to bond with this one and this one. That's 2, 3, 4, 5, 6. And you go to this one, 1, 2, 3, 4, and you have the ones that bond, 5 and 6. To double check your work, you see if you complete the. For this particular problem, it's asking us to write the Lewis structure for ammonia, or nitrogen trihydride. The name says it, nitrogen and 3 hydrogens, NH3. First thing we do is we're going to separate and we're going to take the valence electrons. From your periodic table, you know that nitrogen has 5 and hydrogen has 3. When you add those up, you have 8 electrons. So you're going to start with the smallest one because they're all going to surround it. So you're going to have nitrogen by itself. And you know that hydrogens are going to surround it. You know that nitrogen has 1, 2, 3, 4, 5. Once you have your Lewis dot symbol, which is this right here, you know that this is going to create a force that's going to push all these down. So it's going to create the effect of kind of like a tripod. The angle you will have here will be an angle of 107 degrees. And since it's kind of like a tripod, it's kind of be in 3-dimensional. So it's going to be one going towards you, and the other one going towards the back, and the other one going the opposite direction. And this is the force. Today's question is, which of the elements listed below has the greatest electronegativity? We have A, selenium, B, antimony, C, potassium, D, gallium, and E, iron. First thing you gotta do is locate where all of them are at. So you know that selenium is Se, which is located right here. And then you have antimony, which is Sb, just located right under it. Then you have potassium, just K, it's all the way over here on this side. And you have gallium and iron. Gallium is Ga, which is right here, and iron, it's a little bit more to the left, it's right here. So one thing you want to remember is that the most electronegativity, the element with the most electronegativity is fluorine, which is right here. So anything that's really close to it has a high electronegativity. So the question was, which of the elements listed below has the greatest electronegativity? So it's just going to be the question today is the equilibrium constant for the reaction Ni plus 4CO goes into NiCO4 is 5.0 times 10 to the 4th at 25 degrees Celsius. What is the equilibrium constant for the reaction NiCO4 goes to Ni plus 4CO? So the thing to remember here is that your equilibrium constant is just your products over your reactants. And if you see the first equation and your second one, it's just swapping places, which means if you had K, once it swaps, you will now have 1 over K. So your new K will be 1 over K. They give you the first equilibrium constant, so it'll be 1 over the given equilibrium constant of 5.0 times 10 to the 4th. So the problem states 2.50 moles of NaCl was placed in a 2.50 liter reaction vessel at 400 degrees Celsius. After equilibrium was established, it was found that 28% of the NaCl had dissociated according to the equation. 2NaCl dissociates into 2NO plus Cl2. Calculate the equilibrium constant Kc for the reaction. The first thing we're going to do is we're going to find out how much NaCl was left and how many moles reacted. So for the NaCl that was left, we're going to have the opposite, what was left over from the 28%, so that's going to be 100 minus 28 gives us 72%. So it's going to be 0.72 times the actual moles that we had, which is 2.50. This is going to give us a total of 1.8 moles. Then we're going to see how many moles reacted. Which is your actual 28% times again the moles that you had. That gives us a total of 0.70 moles. We're going to take a look into the stoichiometry for NO and for Cl2 using these moles that we got that actually reacted. So we have 0.70 moles of NaCl and if you see NO over here, we have 2, so it's 2 moles. So 2 moles NO over 2 moles, again 2 moles over here of NaCl. To cancel out the NaCl, we get 0.70 moles once again. Do the same thing over here for the Cl2. Right here you only have 1 mole, so we 1 mole of Cl2 over the 2 moles of your reactants, which is NaCl. This would give us a total of 0.35 moles. Now, having this, you can start to calculate the concentrations. So putting this into the calculator, we get 0.72 moles, molar for NaCl, 0.28 for NO, and 0.14 for Cl2. Now using our Kc formula, which is your products over your reactants, we're going to have reactants, which is NO. Then we have 2 here, so it's going to be squared times your reactants, Cl2, over, now the same thing here because we have a 2, we have NaCl squared. So plugging our numbers for NO, it's right here, I have 0.28 squared times your Cl, 0.14, all over 0.72 squared. What is the hydroxide ion concentration in an aqueous solution with a pH of 6.389? So the first thing you're gonna have to do is you're gonna get the equation for pH, which is pH plus POH is 14. They're already giving you the pH, so you plug it directly. Solving for the POH, you have to subtract this on both sides. And you end up with 7.611. You know that POH, solving for it, is 10 to the negative POH. So if you plug this into your calculator, what is the H plus concentration in an aqueous solution in which OH equals 1.2 times 10 to the negative 5 molar? First thing you're going to have to do is write down the formula. 10 to the negative 14 equals your OH ion times your H plus. They're already giving us the OH, which is 1.2 times 10 to the negative 5. Solving for H, you'll get, what is the pH of 675 milliliters aqueous solution containing a 0.036 moles of NaOH? First thing you're going to have to do is find the moles that you have. It's dividing your moles they give you with liters. You got to be careful. You have milliliters here, convert into liters, 0.675 liters. So you're going to have 0.036 over 0.675 moles here, and you have liters. That will give you a total of 0.0533. Now, getting the negative log of that, just convert it into scientific form, it gives you 1.27. Now you gotta be careful, you're not done yet. You have to subtract it from. What is the pH of 15 milliliters of 0.0045 moles of HNO3? So right here they're already giving you the value. So all you gotta do is plug it into the formula, which is pH equals the negative log of the moles you have, so it's 0.0045. Solving. What is the pH of a 2.5 times 10 to the negative 2 molarity acetic acid solution with a Ka of acetic acid of 1.8 times 10 to the negative 5? First thing you want to do is write the solution for acetic acid, which is C2H4O2, and you want to see what it disassociates into. So you have your hydrogen ion plus C2H, now it's 3 because you take away one H, so it's H3O2 negative. Doing your ice equation, your ice table, you're telling you that it disassociates 2.5 times 10 to the negative 2 moles. So, here you start with 0. Since it's disassociating here, it's going to be negative X, and it's converting over here, so it's plus X plus X. So you end up with 2.5 times 10 to the negative 2 minus X. You have plus X here, plus X here. Putting it into the formula of products over reactants, you get X squared over this. Since the change in this X is very minimal, you can actually disregard it. So this is the only formula that you have. And you know that this equals to Ka. They're already giving you the value of Ka, so you just plug it in. Now solving for X, you're going to multiply this times the 2.5 times 10 to the negative 2 and get the square root of that to solve for X. Solving for it gives you 6.71 times 10 to the negative 4. A 0.10 molality solution of an acid, HA, has a pH of 3.0. What is the Kb of the conjugate base A negative of this acid? So the first thing you want to do is write the solution you have. So you have HA. You know that strong acid, so it dissociates completely. So it's H plus A negative. Here you're gonna have your H ion. You know that it equals 10 to the negative pH, and they're already giving you a pH of 3. So you gotta do is plug it in. 10 to the negative 3. So you know that your H concentration will be 1 times 10 to the negative 3. Now if you do an ice table for this, you're going to have your 0.1 here, which is what they're giving you over here, 0.10. And then you start with nothing. And it's going to disassociate. It's going to get added. So at the end you have 0.1 minus x plus x plus x. So you know that Ka equals your H plus times your A negative, because it's your products or your reactants, and using this equation right here, you know you're going to have x squared over 0.1 minus x. We said before it's just so small that you can disregard it, so you're going to have x squared over 0.1. You already have your hydroxide ion concentration, which we solved for it on this side over here. So you just plug it in. It's 1 times 10 to the negative 3rd. And since you know it dissociates completely, you know that A negative is going to be the same. So it's 1 times 10 to the negative 3rd. That's why this is x squared. And down here you're going to have 0.1. Solving for this, we get 1 times 10 to the negative 5. Now you gotta be careful because this is Ka, and they're asking us to solve for Kb. So you get the formula from your water, just Kw equals Ka. So the question here is, what is the pH of a sodium formic acid buffer solution containing equal concentrations of both buffer compounds? The important thing here is that it's equal concentrations of both buffer compounds. So you know that the formula for pH, which is what they're asking for, is pKa plus the log of your conjugate base over your acid. But you know here that it's equal concentrations on both buffer compounds. So you could just assume one number, because if you have 2, you're going to have 2 on the other side. If you have 1, you're going to have 1 on the other side. So let's just assume that it's 2. So if you have log of 2 over 2, you end up with log of 1. And we know that log of 1 equals 0. So this whole part here is going to equal 0. So we know that our pH is equal to pKa. And we're giving the Ka of formic acid. And The only thing you have to do to turn Ka into pKa is get the negative log. So if you get the negative log of 1.7 times 10 to the negative 4, what is the H plus concentration in a 5.7 times 10 to the negative 3 molality of CaOH2 solution, or calcium hydroxide? We know that this is a strong base, so if we write the solution to it, we have CaOH2. This associates into Ca2 plus 2OH negative. Since it's a strong base, you know that it's going to dissociate completely to the other side. So if you have 5.7 times 10 to the negative third on this side, you're going to have the same thing here. But right here, it's dissolving twice as fast. So you're going to have 5.7 times 10 to the negative third. Now I'm just going to write them again, solving for the new 2 times 5.7 times 10 to the negative third. If you plug this into your calculator, you get that it's 1.14 times 10 to the negative 2. Remember, all this is in molarity. If you plug this into your equation, you know that this is your OH concentration, so you know that OH is this. And you plug it into your concentration of 10 to the negative 14 equals OH times your H concentration. Which one is smaller? So it's attached on the third carbon chain, so you know it's going to be 3-methyl-1-pentene. And that's it. In this problem, it's asking us to identify the conjugate base of HSO4 negative in the reaction of H2PO4 negative plus HSO4 negative dissociates into H3PO4 plus SO4 2 negative. So it's just asking us for this particular one. So all we gotta do is pull it out of the equation and disassociate it by itself. So if this is your acid, you know that this is going to be your conjugate base. This particular problem, it's asking us to identify the conjugate base of CH3COOH in the reaction CH3COOH plus HSO4 negative disassociates into H2SO4 plus CH3COO negative. So same as the last problem, it's asking us for this particular one, so we're just gonna take it out of the equation once again. And disassociate it. So we want to take out a hydrogen with a hydrogen ion, and this will leave you with, so if this is your acid, you know that this is your conjugate base. This particular problem, it's asking us to calculate the pH of a 1.6 molality KOH solution. So you have to remember one thing, the formula for POH, which is the negative log of your OH. Getting what they give you in the problem, plugging it in, so it's negative log of 1.6 Solving for that, it gives you negative 0.204. You plug it into your pH formula, which is pH is equal to 14 minus your pOH that you just solved for. Plugging in, we get that it has a pH of 14.21. That's right.